Hello everyone, my name is Liang. I'm a researcher from ISCS. Today I will present our work, One Simple API Can Cause Hundreds of Bugs, an analysis of Refcounting bugs in all modern Linux kernels. This is a joint work with Tsinghua University and CNITSEC. Refcounting is proposed to automatically manage heap objects. To implement it, programmers need to consider three things. The first one is the ref counter, which is used to record the reference number. The other two things are the increasing and the decreasing API that operate the ref counter. Specifically, whenever there is a new reference created and an old reference destroyed, the API should be invoked. Specifically, when the ref counter becomes 0, which means there is no any other reference, the object should be released. Based on our observation, refcounting is still widely used in Linux kernel. It's reported that more than 90% of kernel fields involve refcounting behaviors. Consider the performance. Programmers prefer to manually invoke the related APIs, and they also do many optimization. Here is an explanation about the optimization of the memory policy refcounting. Unfortunately, it is the manual invocation and the optimization that make Linux kernels suffering from more and more refcounting bugs. Only in last years, there are about 200 bugs. In this work, we focus on two main kinds of refcounting bugs. The first one is the refcounting. In these cases, programmers miss the increment or decrement that should have been done for a reference creation or destruction. The second type is the misplacing refcounting. In these cases, programmers do not place the increment or decrement API into the proper locations. To detect the refcounting bugs, many solutions have been proposed, and three main strategies are applied. The first one is inconsistent refcounting. It requires the programmer to add a paired decrement whenever there is an increment. The second one is invariable analysis. It requires the number of created or destroyed reference should be equal to the number of ref counter. The last one is cross-checking. It needs to detect abnormal refcounting behavior as refcounting bugs. Here we list all the related work on refcounting detection. So in this work, our question is, given so many detection solutions, why there are still so many refcounting bugs reported, and what are the characteristics or root causes of these bugs, and what can be done to proactively reduce or eliminate these bugs. So our goal are following. The first one is we want to understand the security impact of these bugs. The second one is we want to explore the distribution and the lifetime of these bugs. The last one is we want to infer meaningful root causes and which can help us propose anti-patterns to detect new bugs. To achieve above goals, we collect more than 1 million commits from all kernel releases, and we use two-level filtering methods to identify the refcounting bugs. Finally, we collect 1,033 refcounting bugs as our dataset. Well, we cannot identify the bug without any words in their commits, but we try to solve the potential for the positives introduced by the wrong patches. Specifically, we use the fixed tag attached in the commits to identify the wrong patches. Based on the dataset study, we find some interesting. The first two findings are about the security impacts. Specifically, there are about 71% of the study bugs can introduce memory leak, and others can lead to the UF bugs. It's also surprising that more than half of the bugs can be detected with simple intra-ampere analysis. The other finding is about the distribution and the lifetime. First, the third finding told us that the Refcounting bug meets the long-tail distribution, which is consistent with a previous work which aimed on other system errors. The fourth finding told us that about 75% of the bug need more than 1 year to be fixed, and there are even 19 bugs exist more than 10 years. The main reason is that Refcounting bugs are actually a special kind of semantic errors, which can hardly be detected by current fuzzing-based methods. The last finding told us that there are about 23 bugs that exist from the first major releases to the recent ones. Okay, let's introduce our main contribution of this work. It's the root causes of the Refcounting bugs. First of all, we introduce the semantic templates that can describe the root causes of the bugs. It contains two things, the semantic operator and the context. We use different symbols to mean the different things. In this table, we use the template to describe the two main types of Refcounting bugs. Okay, the first main reason of the counting bug is so-called implementation division, and it contains two subtypes. The first one is the return error problem. It's a common sense that a function will not do any Refcounting operation, even if some error is met. However, based on our study, we find special cases. For example, in the PM runtime suspend function, it will complete the increasing operation even there is an error is met. Unfortunately, the caller will not easily catch subtle division, and it will directly return out without any consideration of the paired decreasing. So a potential memory leak is introduced. The second subtype of division is a return none problem. In most cases, the Refcounting API will only return non-empty pointer, and the caller will not add unnecessary non-check. However, for the special cases, here we use the mDescribeGrab. This function will potentially return non-pointer if the global variable is empty. So the caller without any non-check will finally introduce the non-pointer dereference problem. The second main reason is the hidden problem. It also contains two subtypes. The first one is the complete hidden problem. In these cases, we identify the smart loop, in which cases the programmer will add a increasing API in the beginning and add a decreasing API in the ending of the iteration. Both of them are totally hidden for the user. So, when there is a break from the iteration, the caller will not any paired decreasing API, so a potential memory leak is introduced. The second type is a partial hidden problem. For these ones, we collect the buggy API's name and calculate the semantic similarity with Refcounting. From table, we can see that all of them have very low semantic similarity with Refcounting. It can explain that for these buggy APIs, the caller will not easily realize the existence of Refcounting behaviors. The third main kind of the root causes is we call overlooked locations. It contains 3 subtypes. The first one is the arrow handle problem. For a function, there usually contains 2 passes. In the normal one, the programmer will return a ref-counted object. In the arrow pass, the programmer usually only focuses on the resource relation, but without consider the paired decreasing API. The second one is we called indirect call problem. The programmer will usually prepare functions in the driver initialization, and they usually only add the increasing API in the one function, but forget the decreasing in another paired function. The third overlooked location is the direct-free problem. In these cases, we use the CB as a allocated object and is assigned to another ref-counted object CA with a proper ref-count increasing API. However, the programmer will directly free the CA without any chance to call the ref-count decreasing API of the CB. The final root causes of ref-counting is so-called future risk. It also contains 2 subtypes. The first one is a potential delocation. In these cases, the programmer prefers to call the ref-count decreasing before the pointer accesses, as they think there are the ref-count increasing before the function, so they can confirm the safety. However, we cannot stop the future development, which will introduce new module where the function is called without any ref-counting increasing. The second type is the reference escape problem. In these cases, the programmer will call the ref-count increasing before each escape function. However, they cannot stop new module where the escape function is called without any ref-count increasing. In both cases, a potential UF bug will be introduced. Based on above root causes, we propose 9 anti-patterns, and we also designed and implemented 9 static checkers based on the templates. Specifically, we use PLY-based lecture tool to identify critical semantic operator, and we use Zhang-based graph analyzer to generate AST and identify some operator and all of the contexts. With this 9 static checker, we detect ref-counting bugs in recent kernel releases. Finally, we identify more than 300 new bugs and more than 200 bugs confirmed. We have open sourced our checker in the GitHub. Welcome for any questions, and thank you for your listening.
Hello, I'm Jerry from UBC. Really interesting work. I recognize a lot of pattern in drivers. I feel like your work shows a strong evidence that we really need to rewrite Linux kernel, part of the Linux kernel in C++ or Rust, because lots of these bugs can be eliminated by the standard library like the C++ RAII or the Rust drop trait. I wonder what's your opinion on that?
Thank you for your question. I think the developer should read this paper and to avoid the buggy pattern. For the Rust, sorry, I know little. Sorry.
Okay.
Thank you.
Okay, we have no other questions. Yep, okay.
Hello, Petros Maniatis, Google.
Hello.
I was wondering if you could say a little bit about the false positives you found. Was there something in the patterns that was too permissive and allowed the false positives to happen? How did they occur?
It's about our method on the AST. If some bug is the increasing or decreasing with assignment in the same line, this will some false positive. I will fix them in the future work. Thank you.
Thank you.
Thank you.
Okay, I think someone is rushing there to the mic, yes?
Ding Yuan from University of Toronto. A very interesting work and especially impressive to see like you found hundreds of bugs from Linux kernel. My question is that when you report those bugs to the Linux developers, you show there are 200 of them confirmed. How many of them are fixed? Basically, maybe that's a good indicator that which bugs are more important, more urgent, that they have to fix it right away. Thank you.
Okay, thank you. Thank you for your question. There are indeed some response for a long time. Until now, I receive a new response from the developer. They are totally dependent on the developer based on their time. Thank you.
Okay, no more questions. I can just add that I find these results scary. Something is wrong with the way we build operating systems. We need to do better. Let's thank the speaker.